Tonight, you look up at the stars and everything seems calm. Every star appears fixed, every second feels ordinary. But the real answer is far stranger. Somewhere in the universe, time is flowing at a completely different speed. Near a black hole, a single hour can mean years for someone far away. That sounds impossible because your brain treats time like a universal clock. You expect 1 second to be 1 second everywhere, but the universe never promised that. Time is part of the fabric of space itself, and gravity can stretch that fabric. More than a century ago, Albert Einstein proposed the theory of general relativity. Instead of thinking of gravity as an invisible force pulling objects together, he described it as the bending of space and time. Imagine placing a heavy bowling ball on a trampoline. The surface curves. Roll a marble nearby, and it follows the curve. Planets move around stars in a similar way, not because they are being pulled by invisible ropes, but because they are following the curves in spacetime. Now imagine making that bowling ball heavier and heavier until the curve becomes unbelievably deep. That is what happens around a black hole. A massive star runs out of fuel, collapses under its own gravity, and squeezes enormous mass into an incredibly tiny region. The result is an object so dense that even light cannot escape once it passes the event horizon. The closer you get to this immense gravity, the slower time passes compared with someone farther away. This effect is called gravitational time dilation. It is not science fiction. It is real physics, tested countless times. In fact, you already rely on it every day. GPS satellites orbit Earth where gravity is slightly weaker than it is on the ground. Their clocks tick a little faster than clocks on Earth's surface. Engineers constantly correct for this tiny difference. Without those corrections, your navigation would drift by kilometers within a single day. Now imagine replacing Earth with a black hole. The effect becomes enormous. Suppose you board a spacecraft and carefully approach a supermassive black hole. From your point of view, everything feels normal. Your heartbeat is steady. Your watch ticks exactly once every second. Nothing about your own experience tells you that time has changed, but someone watching from far away sees something completely different. They watch your clock slow down. Your movements become slower and slower. The light from your spacecraft stretches toward red. Eventually, you seem almost frozen at the edge of the event horizon. Who is right? Surprisingly, both of you. You experience your own time normally because your brain, your heartbeat, and your watch are all slowed together. The distant observer compares your clock with theirs, revealing the difference. In Einstein's universe, time depends on where you are. Physicists such as Kip Thorne and Roger Penrose spent decades exploring these strange consequences. Their work helped explain black holes, warped spacetime, and some of the most extreme environments in the cosmos. Many people first encountered this idea in the film Interstellar. On Miller's planet, 1 hour equals 7 years back on the spacecraft. Although the story is fictional, the science behind the time dilation was carefully calculated using real physics. Could you survive crossing the event horizon? If the black hole is supermassive, you might not notice the crossing itself. The true danger comes deeper inside, where gravity changes so dramatically from head to toe that it would eventually stretch anything apart in a process nicknamed spaghettification. Black holes continue to challenge everything you assume about reality. They remind you that time is not fixed. It bends, stretches, and changes with gravity. The next time you step outside on a quiet night, look at the stars again. Somewhere beyond that darkness, clocks are ticking at different speeds. Journeys are unfolding on different timelines, and the universe is quietly proving that time is far stranger than it feels.